Good morning. We are group number 2 and we are going to present you our poem design project, a conceptual design. We're going to give you some context in the introduction, goals, pump specifications, physics, results and analysis, comparison with the manufacturer, and conclusion. Pumps are the most economical and most common turbo machinery used for pumping water and other substances in industrial applications such as food processing and chemistry mass production. We are going to model a centrifugal pump because there are three types, and the idea is that we model an ideal part of the centrifugal pump. Knowing the great benefits of pumps in the industry, it is decided to design and simulate a pump with a proposal geometry based on the manufacturer's specifications. Moreover, determine and specify an operation curve, knowing the objectives next to them.
Now we are going to explain the design parameters that we use for our pump. For the impeller, we first of all establish the outlet diameter, that is the same value that the manufacturer has for the impeller diameter. And after that, based on the information that we obtained, we calculate the inlet diameter, the inlet blade width, the outlet blade width, the inlet and outlet blade angle, and the number of blades. Some important parameters that we obtained from the manufacturer that we're going to use are the nominal head, the nominal flow rate, and thanks to our calculus, we obtained the specific speed.
Regarding the geometry of the pump, we will start with the impeller. As we can see in the plans, the impeller has an external diameter of 308 millimeters, 6 blades, and a thickness of 6 millimeters with which the blade offset was made. In the volute, we have a discharge diameter of 65 millimeters, a suction diameter of 80 millimeters, a nozzle distance of 15 centimeters, and a softened cold water. Finally, we can see the assembly of the volute and impeller. In this assembly, you can see a 4 millimeters side clearance.
The most relevant mesh parameters were the base size, the minimum surface size, that it depends on the type of mesh that we were making. In the case of the base mesh was 8%, but it changed if we wanted more or less cells. The target surface size was 2 centimeters, the same as the base size. The number of bridge layers was 5, and the number of thin layers was 3. After applying these parameters, we obtain three types of mesh, and then we use the nominal head provided by the manufacturer for simulating its behavior. We obtain these results for YLG plus efficiency and total head, and we compare them with the head and efficiency provided by the manufacturer through an MSE. As we can see, the MSE for the head is the lowest in the base mesh, and that means that it's closer to the head report by the manufacturer. Also, we can see that the highest efficiency was given by the base mesh. That's why we decide that it's the most suitable for our pump. For evidence the difference between these two mesh, we have selected different views. First of them is the meridional profile. Here we can see the prims layers and the difference in the quantity of cells of each mesh due to the minimum surface size. Also in this isometric view, we can evidence the difference between the mesh due to its quantity and size. Finally, we can evidentiate the frames layer and the difference in the base size of each mesh in the cut water and the blades.
Now we'll talk about the physics. Here we have the fluid properties for the substances used in the simulation. The Reynolds number calculated for both substances is greater than 2300. This is why the models are for a turbulent flow. First, we chose a constant density since they are incompressible fluids. We're taking the gravity a steady state. We use the K epsilon turbulence model. We use the Navier-Stokes equation. Our coordinates are centered in the origin, with y pointing at the inlet and z pointing at the outlet. Results and analysis. Here we have the total head comparison between the manufacturer and our simulations. We can see that the manufacturer shows a rate of flow behavior compared to the water of our simulation that shows a mixed flow behavior. This might be because of the geometry and the changes we did to the pump. Here we have the comparison of the efficiency between our simulations and the manufacturer. We can see that the water simulation has a higher peak of efficiency than the manufacturer. Also, the mineral oil shows the lowest efficiency since it has more viscosity, and this causes greater losses of energy inside the pump. For the brake power of our simulations, as flow rate increases, the brake power also increases. For the hydraulic power, as flow rate increases, the hydraulic power also increases, but it decreases the rate at which it does because the total head decreases as flow rate increases. Since worldwide plus is correlated to the Reynolds number, we can see that mineral oil has much less worldwide plus than water. For water cavitation scene, we know that water at 20 degrees Celsius has a vapor pressure of 2,330 pascals. For flow rate of 0, it has no cavitation, but as flow rate increases, the cavitation starts to begin in the eye of the impeller. We can see that flow rate increases and cavitation also increases. This is the water cavitation for our BEP. Now for mineral oil, vapor pressure is at 100 pascals. We can see that at 0 it has no cavitation, but as flow rate increases, cavitation starts to begin at the eye of the impeller. Although there is cavitation, there is less than in the water scenes. This is the cavitation for the mineral oil BEP.
With the function of absolute total pressure, we are seeing the ascent to water with the minimum of its vapor pressure. And we are seeing that the pressure is lower in inlet and higher in the outlet. In this sense, we note that the pressure is elevating in the outlet zone. In the best efficiency point, we are seeing that the pressure is elevating. In the other part, with mineral oil, we are seeing that the minimum pressure is through 100 pascals, which is the minimum pressure of mineral. In comparison with the first sense with lower flow rates, we are seeing that the pressure is elevating again. In our best efficiency point, the pressure again is elevating, and in comparison to water, it is elevating more.
In the water wallway plus essence, we can observe that as the flow increases, the areas in which the wallway plus approaches zero increase. This occurs because as the flow increases, the flow velocity increases too, and therefore the kinetic energy changes. Now, in the sense of the wallway plus of the mineral oil, you will see that in each flow, the wallway plus will be the same, and this will have a value of zero because of the oil. Oil is a more viscous fluid, so the relationship between wallway plus and fluid displacement is lower.
Let's continue with the scenes. Now we have the water velocity magnitude, and here we have an image that shows us the velocity magnitude in all the flow rates. Continue with the magnitude of the mineral oil. We have that in every flow rate we have the same velocity as we already said in water, but in this case it shows us that is correct because we need to have the same velocity in the place because that's the main reason of a turbo machine. Continue with the scenes. Now we have the velocity vector for the water. In this case, for 0 and 19. Now we have 182 and 210 flow rates. Finally, we have the flow rate for 220. That was our best efficient point, our BEP. And basically, in this case, we can see in all the trenches for the water that the velocity vector lines are increasing inside the pump. Let's continue with the velocity vector for the mineral oil. Continue with the velocity vector of the mineral oil. We use the same flow rates as we already use in water because are the values that the manufacturer already gave us. For the last of the velocity vector for mineral oil, we have our B best efficient point, our that was 119. And in this case, as we already concluded in water, we can see that if we increase the flow rates, we can see more velocity vectors inside the pump. Finally, as the video shows us, the final scene of the water, we can see the whole path inside the pump of the water. Finally, we have our last scene, in this case for the mineral oil, and as we already saw, in the water, in this case, is the same thing. The whole path that the mineral oil have inside the pump.
For our conclusions, we found out that our pump had mixed flow instead of rate of flow, and it was more efficient than the manufacturer's pump. Comparing the substances we use, water and oil, the pump works better for water, since it's less viscous than oil. The difficulties that we came across during the project were the simple details that could cause the simulation to give wrong values and the interpretation of the results. The project was an opportunity to the approach of the design of a pump, understanding both the theory and the practice. Although there were many simplifications in the pump, we could get results that were very precise approximation to real-life pumps, such as the manufacturers.